How's it going? Today we're going to talk a little bit about how we measure the sound that we work with in audio. We have this delightful measurement that we've developed over the years. It's quite handy, and it's called the decibel. We apply it in lots of different ways, different versions of the decibel, and it's not even really a very precise kind of a measurement. It's never really meant to be a precise measurement. It's an odd thing measuring something that relies on the way that human hearing works, because human hearing is not a linear function. Where does the decibel begin? And let's go back to the very beginning, which in all things audio always starts with the telephone system and Alexander Graham Bell. So we start running out telephone lines, and at some point people start realizing, well, we need to figure out some kind of way to describe the gains and losses in signal power within the system. So when we have several miles of transmission cable, obviously there's a loss of power, a loss of signal. How can we measure that loss of signal so that we can then replace that power down the road and put booster amps into the line and compensate for that? There became this need to create a unit to express that loss of power over a mile. So they came up with the MSC, the mile of standard cable. This unit becomes replaced by what they call the transmission unit. And the way that they figured out the transmission unit was 10 times the logarithm of the measured power to the reference power. That ratio, take the logarithm of that, multiply that by 10, and that gives us the number for our unit. Over time, they decided, let's honor that great old gentleman, Alexander Graham Bell, and let's call this transmission unit the bell. The bell actually is the logarithm of the ratio to the measured power. But they decided all of our numbers would end up being smaller if we just multiply that by 10, and we call it the decibel. Then the numbers end up being from 0 to like 120, 130, and they're more manageable numbers as it turns out. We come up with the decibel instead of the bell. It gives us a better range to deal with our numbers for what we're trying to do. This was originally a unit of measurement for transmission cables. This is also a way that we can measure actual sound power, the actual level of sound power and acoustic power, as well as any kind of voltages that we're using for sound. So it all comes down to using the logarithm. What is a logarithm and why a logarithm? The reason why is because it better describes the gradations of human hearing in a way that makes sense. The threshold of hearing, the very lowest thing that we can hear, is about a trillionth of a watt of power. The most loud thing that we can handle is about 1 watt of acoustic power. So there's this great big difference between 1 trillionth of a watt to 1 watt. There's all these parts in between: soft, medium, loud, forte, pianissimo, mezzo forte, forte. I mean, we got to figure out the numbers for those too. It's not linear. It takes 10 times the power to double the volume of something. We need to sort of control these numbers that go from 1 trillionth to 1 watt. Logarithms function very well for this. And what a logarithm actually is, it is an exponent to which we raise a certain number, or a base, to get a result. And the base can be any number, but in our application, our base number is the common log of 10. If I want to take the logarithm of 100, for instance, and we're using base 10, 100 equals 10 squared. So the log of 100 is going to be 2. Because 10 to the 2 equals 100. The logarithm of 1,000 is 10 to the third, so we get 3. The logarithm of a trillion ends up being 12. Now we can sort of manage these numbers. There's also negative logs. If we have a negative number, then this is that number divided by 1. The logarithmic scales works to describe how human hearing responds to changes in levels. It's the best way to do it. Ultimately, a decibel is not a number unto itself. It expresses a ratio between 2 powers. A decibel doesn't sort of exist in space. It presents itself as the ratio of a measured power to a reference power. So for instance, when we're talking about human hearing, we know there's a trillion to 1 range, and the threshold of hearing to the threshold of pain from 10 to the negative 12th to 1 watt per meter squared. The decibel can represent that range. 10 times the logarithm of a trillion to 1 equals 120 dB. From the softest thing we can hear is like 1 dB to the loudest thing we can hear, and that's the threshold of pain, 120 dB. Obviously, we can get louder than that, but as far as our needs are concerned, for hearing, 120 dB range works great. So here's a couple of observations I want to make about decibels that sort of help you sort of realize how we can use them. Number one, it takes a tenfold change in power to sound twice as loud. Also, a tenfold increase in power means you've got up 10 dB. So 10 times the power, go up 10 dB, sounds twice as loud. When you double the power, you get a 3 dB increase. Take half of your power, you end up with a 3 dB decrease. And let's talk about the inverse square law just for a second. The intensity of a sound is proportional to the inverse of the square of its distance away. Every time that we double the distance from a sound source, we're going to see a drop in 6 dB every time that we double our distance. If we add and subtract dB, it's almost like we're multiplying the power, just like we're working with any kind of exponent. And here's some useful common laws. The log of 0.1 is -1, for instance. The log of 1 is 0. That means there's no change in the ratio of the measured power to the reference power. That no change, 0 dB. And here's some other numbers, the log 2, log 3, log 5. These can be sort of handy things just to familiarize yourself with. All right, let's talk about what we mean by sound power and sound intensity. They're different because sound intensity is watts per meter squared and sound power is just watts. Sound power is just the raw power that goes into making the sound, just the raw freaking acoustic power. For sound intensity, for watts per meter squared, it's also a 10 log thing, and both of these equations refer as their reference to 10 to the negative 12 watts. As a result, their numbers end up becoming the same. Your sound intensity level and your sound power numbers are going to be pretty much the same because they refer to the same number. But they do refer to two different things. The sound power is the actual power that is taken to get the sound to that point, and the sound intensity level is the actual manifestation of the volume. The best way we can describe this is the difference between electrical power that powers the heat in your room and the actual temperature of the room that results from it. That's the best way we can sort of make that analogy between sound intensity and sound power. Both refer to 10 to the negative 12 watts or watts per meter squared. So that would be our bottom number, our reference power. Whatever measured power on top of that would refer to that. We would then take the log of that to figure it out. What's a good way to have a reference of this? The drop of a pin, that's about 10 dB. SIL. Typical library, about 40 dB. Typical conversation, about 60 dB. Control room monitor level when you're mixing at a pretty decent level, 80 to 90 dB. Your average rock concert, about 110 dB. 0.1 watts per meter squared. Threshold of pain is about 120 to 130 dB. And then a jet at full blast at 10 meters away would be 150 dB. That would actually be 100 watts per meter squared, and you don't want to do that to yourself. You will not be able to hear anything. You just don't do it. We'll talk a little bit about sound pressure level, because when we're talking about dBs, a lot of times this is what we really are talking about. We're talking about when somebody has a dB meter and they're walking around a club and they're taking readings of it and they're saying, oh, you're at 90 dBs. And you go, oh, wow, that's good. Now you got to turn down. You're at 90 dBs. I mean, what is that referring to? dBs have to refer to something. It's not a number that just exists out in space. dB SPL, we're talking about sound pressure now. And now when we're talking about sound pressure and sound voltage, where previously we were talking about sound power and intensity, we were talking about a 10 log equation. But when we move to pressure and voltage, now these are 20 log equations because power is proportional to the square of the pressure or the voltage. That doubles the 10 log and makes it 20 log. SPL is sound pressure level, and the reference for that is actually 0.0002 pascals or 20 micropascals. And what is a pascal? Pascal is a Newton per meter squared. It's a unit of work. So the sound pressure is actually newtons per meter squared or pascals. The threshold of hearing that we have for that is 20 micropascals. So it's going to be 20 times the logarithm of our measured level versus 0.00002 pascals. Now, do we actually end up doing this math? No, actually we don't. Machines do that for us. We don't really ever have to sort of figure this out so much. We don't ever really know the actual measured level. What we do is we have a device that measures the level, does the math with the pascals, does the logarithm, multiplies it by 20, and gives us our dB number on our meter box. Your machine is calibrating the actual sound pressure of the air and comparing that to 20 micropascals to come up with our dB/SPL. There are also weighing factors you may have heard about with dB/SPL. There was this original idea that we didn't actually have to calibrate to a lot of the low frequency material. We would weight out pretty much below 125 hertz. Well, of course, as time has gone by, we hear that stuff, so we're not going to do A weighting. We tend to C weight now, so that means there's no weighting on our SPL meter from 125 to 2K, and there's a little bit of weighting at the very high. If you hear about A weighting, B weighting, C weighting for SPLs, that's what that means. So that's sound pressure level. Again, that's a 20 log thing. Let's just sort of go through, what are you going to see for decibels? All right, talking about our power decibels. Our 10 log power and intensity decibels, we have first 0 dB milliwatts with a small m. That refers to 0.001 watts as our reference power. It's a 10 log equation, so however many watts we have, do that equation from that to figure out our dBms. Our dBws is a reference to 1 full-on watt, which is of course a lot of acoustic power. So obviously we're going to be talking about loudspeaker assessment for this. We're talking about 1 watt, 10 watts, 100 watts, that kind of numbers of watts. We're talking about loudspeakers because it takes an enormous amount of wattage just to get a loudspeaker to do what it needs to do. You lose over 90% of all of that power just into the air without even getting the sound out of it, just from heat. That equation would be 10 log your measured wattage versus 1 full watt. For voltages now, and moving over to our 20 log equations, we have the dBV. So 0 dBV refers to 1 volt. 0 dBu refers to 0.775 volts. And the way we got to that being different, having the dBV and the dBu, was because when we put 600 ohms across the circuit for our VU meter, that brought us down to 0.775 volts. So we used that for the reference instead. So you can, if you see dBV, it's in reference to 1 volt. If you see dBu, it's in reference to 0.775 volts. You might see the dB small v, and that is a reference to 0.775 volts across 600 ohms as well. That's more of a European thing. You probably wouldn't see that in the States. And then dB microvolt refers to 0.000001 volt. These are for very, very small electrical charges. Again, talking about microphones. So that gives you some idea of some of the different kinds of dBs that we find ourselves coming across, and some dB graphs to look at to sort of give you some reference between the dBu graph, dBFS. There's also dBFS, which is a digital version of dB, which is dB to digital full scale. As you can see, that goes up to 0 at the top there. You can sort of see how these all sort of relate to each other, the dB, SPL, dBW, dBu. Mostly going to be seeing dBu or dBV mixing with faders. Let's talk a little bit more about decibels in terms of consumer versus pro gear. Some of you may have heard that consumer gear has a standard operating level of -10 dBV, and then pro gear has a standard operating level of 4 dBu. And that kind of makes you wonder, well, what does that necessarily mean? And what voltage is represented by -10 dBV? What level difference are we talking about here? If I looked at this, I would probably assume that if I had a signal in my consumer gear, I would have to bring it up 14 dB to have it match with the pro gear. Is that true? Let's find out. -10 dBV. So here's my equation. Here's my knowns. I know that my dBs here are -10 dBV, and I know what my reference is, 1, as far as the volt is concerned, but how many volts are unknown to me? So I need to solve for the V. I bring the 20 over. I've got -0.5 equals log of V. And then I have to do an anti-log on my calculator, 10 to the x on the calculator, to figure out V. So I find that 10 to the -0.5 equals V. That comes out to being 0.316 volts. When I do the same kind of math going on with my dBu, my reference for dBu is not 1 volt, but it's 0.775 volts. So I put that number in there instead. I do the math, so I end up with 0.2 equals log V divided by 0.775. Work the math out with the anti-log, and I end up with 1.228 volts. So that's the actual difference between what consumer gear operates at and Pro Gear operates at. So what's the difference between those two? Let's see now in dBs, what is the difference between these two? We don't know our dBs, but we know what our measured power and our reference power is. Reference power in this case is 0.316. Our measured power was 1.228. We do that little bit of math to get 3.886. We take the log of that and multiply it by 20, and we come up with 11.8, or roughly 12 dB. That's how much we would have to add to a preamplifier to get our minus 10 dBV unit up to the plus 4 unit. Not 14 dB, but 12 dB difference. Do we have to do this kind of math all the time? Hell no. What's important to understand is that it's not an exact measurement. It's really just a way for us to sort of understand how much power we need to use to get what we need to hear in a certain way. When you're mixing, to get something just where you notice the difference, that's about 1 dB. For your average human being that's not at the console, who's sitting maybe somewhere else away from the console, it takes 3 dB of a change to make something noticeable. And that requires twice the power. When we're using the words dB, we're usually using it in terms of 1 dB changes. We're talking about a 3 dB change. We're often talking about a 6 dB change, which again corresponds to our inverse square law. If we double the distance from our source, we go down in 6 dBs each time we double. And then the 10 dB, which of course 10 dBs means that we have something twice as loud, and it takes 10 times the power to get it. Hopefully this gives you some idea of when you start seeing dBs. For instance, if we're going up 10 dBs, what does that really mean? And how does that translate in terms of actual power and actual what we are perceiving in terms of volume? Hopefully this helps sort of get you on the road to understanding the decibel measuring system. Any questions that you have about it, please feel free to ask me. That's all for now. Thanks.